Welcome to the SimCenter's training in uncertainty quantification for natural hazards engineering. Today's session covers the back end of the quoFEM application, as well as capabilities related to the custom finite element method engine. Our speakers today are Dr. Aakash Bangalore Satish. He is a postdoctoral scholar at UC Berkeley. He received his PhD from the Department of Civil and Systems Engineering at Johns Hopkins University. Here at UC Berkeley, he develops methods to quantify uncertainties and update models in natural hazards engineering at the NERI SimCenter. His research interests are in Bayesian estimation and model selection and averaging. We're also joined by Dr. Adam Zsarnóczay. He is a research engineer at the John A. Bloom Earthquake Engineering Center at Stanford University. His work focuses on disaster simulations that support multi-hazard risk assessment and management at a regional scale. At the SimCenter, he is the Associate Director for Research Outreach. He completed his PhD in Civil Engineering at the Budapest University of Technology and Economics, where he was also an assistant professor. His research experience he has research experience working at scales ranging from individual structural members through a building and up to cities with hundreds of thousands of assets. His research interests include probabilistic natural hazards assessment, model development and calibration for structural response estimation and performance assessment, as well as uncertainty quantification in large-scale regional simulations. Adam and Aakash, thank you for being here today, and I think Aakash, we'll start with you.
Thank you, Matt. Thank you everyone for being here today for day 2 of quoFEM's tool training workshop. So yesterday, in yesterday's presentation, Sangri went over an introduction to the SimCenter and introduced the different features of the quoFEM tool. And Sangri also went in detail about surrogate modeling using quoFEM. So if anybody's new here, you might want to refer to those videos if you're interested in surrogate modeling. So the videos will be put up on our website in a few days' time. Today we will go over the custom FEM option in quoFEM and why would you need it, and we'll also give some demos of using ETABS through Python scripts in quoFEM, as well as how you can use quoFEM with existing models that you have developed in Matlab using the custom FEM engine option of quoFEM. So just before we start, I want to again just go over this information. So you will find previous tool training videos and live expert tips recordings in our website. And you will also find detailed setup guide and online documentation. So I wanted to point out to the documentation here. So at our tool homepage, there is the link from where you can download quoFEM. But if you're using Mac, in addition to downloading quoFEM, there is an extra step. You would need to install Python and the required backend packages. So I would encourage you to look at the installation instructions on our online documentation page. And we are very happy to hear from you with any feature requests, as well as bug reports at our SimCenter message board. And today's training material, as well as yesterday's training material, is also available, or it will be available soon. So you can find all the slides as well as all the example files that we'll use in today's demonstration in the Design Safe page. So let me again just, if anybody is new here who hasn't attended yesterday, so quoFEM is a desktop application developed to connect state-of-the-art UQ applications with computational simulation tools. So we use our SimCenter's scientific workflow in order to build several applications, and quoFEM is one such application, which leverages several components coming from the SimCenter's backend. 3 of these are the cloud application, which enables running simulations on cloud computing facilities, cluster computing facilities provided by TAC. And the UQ backend component acts as a preprocessor and a post-processor to UQ engines. So such as the Dakota is one of the UQ engines that are supported in quoFEM. In addition to relying on external applications for UQ, in-house UQ algorithms are also being implemented, and they are part of the UQ engines called as the SimCenter and the UCSD UQ engine. And the FEM component is another important feature of quoFEM. So the FEM component enables, excuse me, enables users to drive simulations using the FEM application of their choice. So OpenSeas is natively supported in quoFEM, and we ship OpenSeas along with the quoFEM tool. But we also natively support running simulations through FEEP or OpenSea Spy. But if you want to do something extra, so if you have models which are not in these FEM simulation engines, so if you want to use something like Matlab, for example, or if you want to run, it needn't even be computational simulation. So if you want to use trained surrogate models coming from other applications, so these are not natively supported in quoFEM, but there is the option of running these through the custom FEM engine, which will be described in more detail later today. So the UQ and optimization task would require several, like commonly hundreds or thousands of evaluations of the computational model. And quoFEM treats the user provided simulation model as a black box. Now the computational models, by treating the computational models as a black box in the quoFEM's workflow, the UQ and optimization methods which are implemented in quoFEM can function across the entire range of supported FEM applications, as well as beyond the range of the supported FEM applications. So this is what enables users to bring in their models, which are in other simulation or surrogate modeling applications, into the framework provided by quoFEM. And yeah, as I said, more details will follow later in today's session. Since the FEM engine is treated as a black box, and the UQ engine drives the simulations through the FEM engine, the inputs and outputs of the simulation are communicated between these engines through text files. So the UQ engine writes the input parameter values to a text file called params.in and expects the outputs to be written to a file called called results.out. So this file should be created by the FEM engine at the end of every model evaluation. This is just an overview of all the available methods to you in quoFEM. There are 5 FEM engines that are part of the FEM component of the SimCenter backend applications. Of these, the OpenSea's FEEP and OpenSea Spy engines correspond to preprocessors that prepare the input for analysis using OpenSea's FEEP or Python, respectively. And the surrogate engine prepares inputs for making predictions using a surrogate model in place of a simulation model. And we'll go into more details as to what the custom FEM engine allows us to do. So in yesterday's session, Sangri went over the OpenSea's FEM engine, as well as she gave a demonstration of how to use the surrogate FEM engine. And several UQ methods were covered in yesterday's session, including Latin hypercube sampling for exploring the parameter, for doing a parameter study, as well as global sensitivity analysis and surrogate modeling. So in today's session, Adam will go over the OpenSea Spy FEM engine, which allows general Python scripts to be run through quoFEM. And later on, the custom FEM engine will be covered. So with that, I will pass the control to Adam. I'll stop sharing my screen.
Thank you, Aakash. Can you hear me well?
Yes.
Is it okay? All right. So let me just share my screen here. Okay, so we will spend a few minutes with the Python option in OpenSeas in quoFEM, which is called OpenSeas Pi, but that's slightly misleading. It's called OpenSeas Pi because that's what it was built in for originally. We wanted to support calculations in OpenSeas Pi, but then we realized that this really allows you to run any kind of Python scripts within a Python environment, and that is a way to access other applications through Python. And this is what I'm going to show you today, because I believe that that's a much wider range of possibilities than just running OpenSeas Pi. But of course, if you have a Python script that prepares a model in OpenSeas Pi, runs an analysis and returns a result, that's also supported by this option. So what we are going to look at today is running an analysis in ETABS. ETABS is a software developed by Computers and Structures Incorporated. It's, I think, pretty widely used in industry, but by no means this example is limited to ETABS. So if you want to run another tool, we have some people who approached us that want to use this for like geotechnical analysis. If you have a specific software that runs those analysis and you can access that through Python, this is an option for you. If you cannot access that software conveniently through Python, I recommend you to listen to Aakash. With the following example, he shows how to access applications through the command line, basically, which is just another option. Okay, so we have two different ways to run external applications. This is just one of them. I have already provided all the codes and scripts that are required to run these examples. One thing I cannot provide you is a license to ETABS. So if you do not have a license, you will not be able to run these examples extensively, but you can download a trial version of ETABS and you can still test them out. You just need to download that trial version yourself. Okay, so let's see what the example is, and we will look at a couple of different uncertainty quantification problems using this example. So we are looking at a 4-story moment frame, where besides the moment frame, we also have diagonal braces. The diagonal braces are there only to represent additional stiffness that is not coming from the frame itself, but from some non-structural elements, for example. And we imagine a scenario where we want to be able to model the response of this frame as accurately as possible. And we recognize that there's this additional stiffness, but we don't really know how much extra stiffness there is. So what we do is we go out, measure the vibration of the frame a couple of times, and we will try to calibrate the additional stiffness that comes from these non-structural elements in the frame, and then hopefully arrive at a better model of the frame in the process. So what we do with these braces, we will have rectangular cross sections, because it really doesn't matter what shape of the cross section has, and we will control their stiffness through a single parameter per brace. B1 through B4 corresponds to the height of that cross section at each floor. So that essentially controls the additional stiffness we assign to each floor in this frame. Now, before moving on, let me quickly show you how this looks like in ETABS. So this is an ETABS application. It's ETABS 19, and this is the model that I prepared. This has been prepared before. This is not prepared through quoFEM or anything like that. I put this together in ETABS and then I save it to a file. And then within quoFEM, what we will do is we will link to a Python script, and I have that on the next slide. And that Python script can access this file. And if you use this template, you would need to update the location of the file on your computer. So we access this file and then do a modal analysis, as you can see in the script here. And at the end of that modal analysis, we will get the vibration periods of the structure, and we will try to match those vibration periods to what we measured on site. Okay, so the main steps are first connecting to ETABS. This is done through a so-called COM interface. This is exclusive to Windows, just like the ETABS application. So those running on a Macintosh would need to emulate a Windows environment, but I think if you are running ETABS, you are used to that anyway. And then within that environment, you can connect to ETABS through Python using this com-types package, which is using the com interface that is built into Windows. And then through that interface, let me pull up that code just to show you a couple of examples of how that works. You can access ETABS, you get this ETABS object, and then you can work with this ETABS object as if it was the application itself. So you can start it, you can see that here, and then initialize a new model, open a file, set cross sections, get masses, run an analysis, and then in the end get the modal periods. So that's what we are doing. We are essentially controlling the application through a Python script. The ETABS API is quite versatile. We are not limited to Python. I just want to mention that. Here is the help that comes with the application. They have examples. It's really well documented, and you can see that it runs through Visual Basic, C++, Matlab, or Python. So there are many options for those who want to run ETABS kind of in batch mode or in these more efficient scripted way. Okay. One thing that is important to remember about this is that it takes about 8 seconds to do one iteration. And because some of these UQ techniques require quite a few iterations, this can take a substantial amount of time through ETABS. That's one of the reasons many people use OpenCs or their own codes for research purposes, because it's just much faster when you have a code that is designed for one single purpose and not such a multi-purpose application like ETABS. So this can take hours to run when you are running a Bayesian calibration that we will show later today in Aakash's example. But for simple things, as you will see, it's much faster because you need only like 10, 20, 50 iterations. Sorry about the noise. Yeah, so let's get into it. So first, let's see what we have measured. We measured 5 times the structural periods. These are the first mode and the second mode periods that we obtained from these measurements. You can see that there's some uncertainty in those results. And if we look at our bare frame without the braces, then the periods are much or substantially, I would say, larger than what we measured. So that already shows us that there must be some additional stiffness in the frame. Otherwise, or the masses are wrong. Something has to be off because these periods don't match. And that's what we are looking for. We are trying to model the first 2 floors in this example, just for the sake of simplicity, so that I can show you some nice 2D plots. So we are trying to model the first 2 floor additional stiffnesses here and understand how much extra stiffness is needed to get from these periods to these. And we will also talk about how to reconcile like the differences between these numbers and how to model that uncertainty. So first, we will explore the response surface and understand how to formulate our objective function for the calibration. This is done through forward propagation. Then we get some quick answers for individual measurements. This is done with deterministic calibration. I will talk more about these first 2, and I will also show you a glimpse of the Bayesian calibration, but Aakash will spend more time on that. So first, let's see the response surface. Whenever you are looking at a problem, if you have the luxury to run a parametric study and look at the response surface, that often tells you a lot about how to formulate the calibration problem itself. So that's what we are going to do now. Here, you can see the response surface modeled through 1,000 model evaluations. So this is quite expensive. Again, remember, it's 8 seconds per evaluation. So this is roughly like 2.5 or 3 hours of calculations through ETABS. Each of these points is the result of a single calculation. And then what we were changing is the stiffness on the first floor and the stiffness on the second floor from these braces. Now let me show you how we run these in quoFEM. So when you open quoFEM, if you download the package for today's tool training, you will find 3 folders, at least in the ETABS example part. There is the ETABS models folder, that's a separate thing, and then the 3 folders correspond to the 3 different examples. So if you go to forward propagation, I prepared an input file so that you don't have to go through providing all the inputs in quoFEM, and you just open this input file and everything will be nicely populated. Now, As I mentioned, we are doing forward propagation now. We use Latin hypercube sampling. I'm limiting this to 5 samples for this example so that you can show that it actually works. But again, the results that you see here are based on 1,000 samples. So just a reminder there. I'm trying to bring quoFEM back to my previous screen. It's harder than I thought. Just give me a second. Interesting. All right, apologies. So quoFEM just evaded me. So we have this forward propagation settings in the first step, and this second step is where we bring in the ETABS approach or the ETABS model. We choose OpenSea's Pi. This model analysis script is what I've shown you already here. So this is where we access ETABS and then run the model analysis and get the periods back. And the parameters file is where we have the unknown parameters that we would like to change in the analysis. This is a single simple text file with B1 and B2 with some initial values. Those initial values don't really matter in this analysis. So we set this up. Here we provide under RV the distribution of the parameters for the forward propagation. We have a uniform distribution between 1 and 100. Again, if you look at this, we go from 1 to 100 here, right? So we are looking at that domain and trying to understand how the B1 and B2 values influence the first mode period and the second mode period of the structure. The colors correspond to the periods. The white results are the ones that are close to our target period, and the red results are lower periods. The blue ones are higher periods. And we are looking at, again, the first mode and the second mode here. So going back to quoFEM, the quantity of interest, we also pulled in the third mode periods here, but we are not using it in the slides. And then when all of this is ready, you just click run, and then it will open ETABS in the background and collect the results for 5 analyses, and then show us the results in the end. While it is running, it will take about 30 seconds to run. Let me go back here and then show you what to do with those periods. So once we see this, we can see that the decisions on B1 and B2 are not going to be very easy, because the values that work for the first mode are not exactly the same that would work well for the second mode. So we have to do some kind of a combination of these two error measures to arrive at an error that we can minimize in the calibration. So first, let's, rather than looking at the absolute value of the periods, let's look at the error compared to some target value. So now I chose a reference value for T1 and T2 from one of the measurements. We have the measurements right here. So I picked the first period for the first measurement for the first period and the second period, and simply looked at the absolute difference between what we have from the model and what we have from the reference. The shape is the same, but the values are different, as you can see. Now we still have one problem here. The first mode period is swinging much more than the second mode period. You can see that the absolute difference goes up to 0.15, while in the second mode period, the differences are smaller. That doesn't mean that they are not as important as the differences in the first mode period. So if we want them to play an equal role during the calibration, we want to make sure that these differences are equal in magnitude. Now, one way to address that is to look at, rather than looking at the absolute difference, we can look at the relative difference in the periods. The first mode is 1 second, and this one is 0.3 seconds. So that's one of the reasons these differences are more significant here. Now, if we look at the relative difference and just take the log of it to convert it to a space where 0 means no error, we get this again. The shape you can see is similar, but the range now is also similar between the two options. So now we are looking at two similar error measures, and now we can combine them and expect that both of them will be considered equally important in the calibration. And that's what we do here, just manually first. So this is still a forward propagation problem, but we are trying to understand the objective function that we will use in the next step. What would be a good way to describe the objective function and describe this calibration problem for us? So we had the error from T1, the error from T2, and we just combined them by taking the log relative errors, summing the squared errors, and taking the square root of that. So SRSS, I think you're probably familiar with this approach. And here on the left, you can see that I wrote a really short Python code to calculate this error for the next step in the calibration. I take the log of the relative error, square it, sum up the two periods, and then take the square root of that, right? So it's really straightforward, I believe. And then what we get if we do this is this plot. So this is now showing the error measure, and you can see that black is the color of when the error is getting close to 0. So this is going to be the area in the input parameter space. So this is still B1 and B2. This is the area where we have the stiffness values that provide good matches with the first measurement that we have. Okay, so now maybe we can go back here. Oh yeah, so I was afraid that this might happen. So ETABS has this tendency to sometimes fail in the middle of the analysis, and then I would have to restart it. Now, rather than restarting it, I would just go on with the presentation. But this is just a visualization problem with the application itself. So this is not something that depends on quoFEM. And in this case, if you restart ETABS and you run it again, it should work. This happens about every 1000th analysis, so it just happens to do it right now. Okay, so once we understand this objective function, we can move on to the deterministic calibration step. And in this case, we will use the script that I have just shown, this one, and calibrate these two parameters. So we will start with an initial value and try to find the values, the two values that will minimize this error term. We do that by choosing the deterministic calibration in quoFEM. I will restart quoFEM to be able to show you this. Apologies, this is ETABS. Matt, maybe. All right, so we are back in quoFEM, and now I will load the inputs for the calibration case. You can see that now we have parameters estimation instead of the forward propagation that we had earlier. We are going to do at most 10 iterations with a convergence tolerance and the time period data that outsets our reference data that we are calibrating to. Because we are using a custom error function right now, let me show you that function. I've just shown it in the presentation to this one. So this part calculates an error and returns the error. In this case, our time period data corresponds to the target error, which is 0. If you wanted to let Dakota calculate the error for you, which will be using a squared error term, an absolute error term, if that's okay, and that's okay in many cases, then you can return the T0 and T1 values, and you don't need to worry about calculating the error yourself. So that's also an option. And then here in the time period data, you would have the reference periods. Okay, this is the same. We are using OpenCSPy. We have a slightly different script, but the same idea. This is the same, and then we have the error term here in the quantities of interest. Okay, if you click run, I'm not gonna test my luck again with ETABS, but if you click run, it should run ETABS in the background, and this is what you should see. We start from the initial point, and then with the blue curve showing our paths through the parameter space, we arrive at another point, which is the optimal point according to our objective function. So here, I enlarged this part just to show you that there's quite a bit of movement here in this space. And we arrive at this point here where B1 is 52, B2 is 16. So this one is the optimal point according to our first measurement. Now, if we change to another measurement, remember that we had a number of measurements here, here. So if we change to another measurement with another target T1 and T2, we would arrive at different B1 and B2. And then the question is, how do we deal with this? Because we can only use, well, at least according to this deterministic option, we can only use one pair of results for our future analysis. And the answer, or one of the possible answers, is Bayesian calibration. And Aakash will talk much more about this, but I just want to show you that Bayesian calibration is available with the Python option also. But as you saw, ETABS is sometimes difficult to run. So running a Bayesian calibration, which requires, in this case, it was 2,800 model evaluations, is sometimes challenging with it. So that's why we are not using that in this example. But you do have the files and you can test your luck with ETABS. And what you see here is, rather than having a single solution, a Bayesian calibration will provide you a range of solutions. If you remember the shape of this error function, it's exactly this banana that we see here that we get back from the Bayesian calibration. So you get a posterior distribution of values where you can see which is more likely, which is less likely, but you have an uncertain probabilistic description of the two parameters that you are looking for. And then you can propagate this uncertainty through your model. And here I'm just showing you, if we sample that distribution for B1 and B2, and then run the analysis, the modal analysis, then these are the periods that we get. This is a distribution of the periods. The 5 red points are our 5 measurements. And what you can see is that we do cover that range that we measured with this probabilistic model. So if we use this model for other types of analysis, we will be able to consider the uncertainty in our measured periods in other types of problems, and the corresponding uncertainty in our model in other types of problems. That's the main idea behind these Bayesian analysis. It's expensive to do, but it gives you a lot more information and a much more robust approach. One more thing I would like to show you, and this is the last thing. You saw some figures here. These are not from quoFEM, but these are not difficult to make. And I included a Jupyter notebook with the files that we uploaded. And here, if it is willing to go full screen, you can see, that's interesting. Yeah, you can see all the code that is required to produce these figures that I had in the presentation. So these are really short, basically just the plotting scripts, and you are able to reproduce them and see how to do this kind of post-processing. And with that, I thank you and I hand it over to Aakash.
Thank you, Adam. Yeah, so continuing from where we left off, so Adam just described how to use, in the example, he described how the response surface was explored and how we can also do deterministic calibration in order to get some quick estimates of parameter values once we have data, and also some idea of what Bayesian calibration can give us. So the point that I would like to just make here is, so with the same model in ETABS, since quoFEM treats the finite element model as a black box, you can use all our UQ algorithms. So with the same model, we are able to do all of these different types of UQ analysis. Now, for the same structure, I will now present an example of using Matlab with quoFEM. To do so, I will use an idealization of this frame, of the braced frame that was modeled in ETABS. So that entire structure is now idealized as just a mass spring system with 4 degrees of freedom. So there are 4 dynamic degrees of freedom, which might correspond to one of the columns here. So there are essentially 4 story stiffnesses and the masses at each story. The story stiffnesses are assumed to have the contributions from the structural as well as the non-structural components. So it is assumed that the non-structural components provide additional stiffness, just as Adam had described in the earlier part of the presentation. So we will also assume that the mass is known and the mass is fixed. So that leaves us with only 3 unknowns after making all of these assumptions that I'm shown on the slide. So it leaves us with 3 unknowns that we would like to estimate. So I'd like to give a demonstration of Bayesian calibration along with Matlab with this example problem. So before that, let me just talk about the custom FEM option. So this option will allow users to specify custom simulation applications. So when we say simulation application, it doesn't necessarily need to be limited to only finite element software, but it can be a surrogate model or a regression model or any other model of that the user wants to use. So with this option, all that the user needs to do is to provide a driver script. Now this driver script to quoFEM will parse the input file generated by the UQ engine, and it will create the inputs as needed by the custom analysis application. Then it will call the custom analysis application with the input. And it will evaluate the custom, the FEM engine will then evaluate the model at the values of inputs that were passed to it. And then it will produce the outputs. Now the driver script should also process the outputs from the analysis, and it should write the results in the format that is required by the UQ engine. So all of these tasks have to be done by the driver script. And that is how you can use custom FEM applications with quoFEM. There are some conditions. The driver script must always be named workflow driver on Mac and Linux, and we should call it workflow driver.pat on Windows systems. So for the example that I just showed you, how would we do this in Matlab? So this shows what the driver script looks like. Let me see if I can. So it's just a very simple one-liner script. So it is just invoking Matlab and running this script in the batch mode. So that's all that the workflow driver script does. So if we then inspect what is inside run eigen analysis, there are these 3 lines. So the first line, we are reading the parameters file that are passed in by the UQ engine to the custom FEM engine. And if we see on the right hand side, so the inputs generated by the UQ engine will always be in a file called params.in, and it will always follow the format that is shown in this example. That is, the first line will specify the number of random variables, while the next lines will contain the name of the random variable and then a space and then the value of the current realization of that random variable. And all that the first script, Matlab script is doing is reading this params.in file, and it is saving the variables in the workspace. Now the second line is running the eigenvalue analysis. So the script on the right hand side is just doing that. So this is the model script that you would start with. In the demo, I will give a more detailed demonstration about of this part. And the third line is just writing the results that are produced from the analysis to a file called results.out. And the format of the results.out should also be as shown here. So it should contain just a single line, and that line should contain all the values of the quantities of interest that we want to obtain from the analysis, separated by space. So this is all that you would need to do in order to interface a custom FEM model written in Matlab in this case with quoFEM. So now I'll switch to a demo. So let me just motivate this demo. So we are given measurements of the time period of the first 2 natural modes of vibration. And this is the same data that Adam had also shown in the previous example. I'll just be using the same data to calibrate these three parameters of this very simplified structure. So the unknowns here are these three parameters, the story stiffnesses. I'll assume that the mass is known. And in Bayesian calibration, we need to prescribe the prior probability distribution for the parameters that we want to estimate. Now, the prior probability distribution is based on all our prior knowledge about the problem, or it codifies all our belief about the parameter values before we have even observed any data. I would now like to switch to Matlab. Adam, do you see Matlab on my screen?
Yes.
Right, thanks for that. Okay, so the run eigen analysis was just the same file that I just described right now. So it has these three lines. Let me first begin by looking at the eigenvalue analysis.m script. So essentially, you would start off with something like this. Now, this script takes there are some variables that you have set in the file, and you are running an eigenvalue analysis by forming the mass and the stiffness matrices and evaluating the solving the eigenvalue problem. And the results that you're finally interested in are the time periods of the first and second mode. So let me just run this to show that this produces an output which consists of all of these. There are 4 modes, and then the results that we're interested in is just the time period of the first and the second mode. Now, so you would start off with something like this, and if you want to interface your model with quoFEM, all you would need to do is let quoFEM know which of these variables will be random variables. And that is done in quoFEM's user interface in the GUI. So quoFEM will then set the values of these random variables for each analysis that it will drive. So you would need to then not have these values in your model script. So I'm just commenting out those 3 lines. Instead, it will get these 3 values from a params.in file that is written by quoFEM. Okay, so now I'll just repeat the same process by stepping through each section of this file. So we see that it is reading in the params.in value, and it is evaluating the time periods, and it is writing it now created the results out of the file. So starting with something like this, we can then use quoFEM to do Bayesian calibration, for example. So I have already preset the values that, by loading, I had already saved the inputs that need to go into this example in a JSON file. And quoFEM lets you open JSON files, which will then populate the different fields that are necessary to solve that particular problem. So in order to do a quick demo, so I'll just set a very small number of samples, and I'll run this using quoFEM. So in this case, we are just requesting 2 samples from the posterior, which is way too small. And while the analysis is running, let me switch back to my presentation. Yeah, so I've set the analysis going, but while the analysis is running, I would like to briefly discuss about Bayesian calibration and what the TMCMC algorithm is doing. So TMCMC is a numerical method that is used to obtain samples from the target distribution, the posterior probability distribution that we're interested in. So this algorithm is inherently parallelizable, and it also is very flexible and works for multimodal density. So that's why we've implemented this in quoFEM. And especially making use of the parallelization is helpful when computing the likelihood function involves evaluating a computationally expensive finite element model. So TMCMC can then be used to effectively sample from the posterior probability distribution by using high performance computing resources because of the inherent parallelizability of the algorithm. So in Bayesian inference, the posterior probability distribution is obtained by applying Bayes rule as I've shown here in this equation. So it is actually typically very hard to sample from the posterior probability distribution because the likelihood needs to be evaluated, needs to be computed after evaluating the model. So we, for a given a parameter's value, we don't, even though we can state it, we don't know the value of the posterior probability distribution. So the idea of TMCMC is to avoid trying to directly sample from the posterior, but instead to sample from a series of intermediate probability distributions that will then approach the target posterior probability distribution in a number of stages. All of these intermediate probability distributions are controlled by what is called as the tempering parameter beta. And at the initial stage, when beta is so at the initial stage, beta is 0, and TMCMC progresses by monotonically increasing beta from a value of 0 to 1. So you can see that when the value of beta is set to 0, so our target distribution would just be equal to the prior probability distribution. So that is what I've shown here. So I have previously run the same example that I wanted to demonstrate in quoFEM before, and I've drawn 500 samples from the posterior probability distribution using TMCMC. But the way that proceeds is in the first stage, there are these 500 samples that are drawn from the prior. The prior, if you recall, I had said to be uniform between 500 to 1500 for K1, K2, and K3, the 3 parameters that we're estimating. So that's what you see here. And then as sampling progresses through these intermediate stages, we see that, so when beta is equal to 1, this is the posterior probability density, and this is our target. But you can see that during the intermediate stages, there is an evolution of the samples from, they're concentrated from being concentrated everywhere in the prior to being a representative set of samples from the posterior. So for that previous example, when beta was equal to 0, this is how the samples look like. And finally, we obtain a set of distributions which would correspond to predictions matching well with the measured data. So here I've shown predictions of the time period of the first and the second period, corresponding to all the samples that were drawn from the prior probability distribution. So we see that there is a wide range in the predictions, and they're not, all of the predictions are not close to the data that we had measured. And in the second figure here, this shows the same posterior set of samples. So this is a pair plot. So it shows the same posterior set of samples with the same limits. You can see that a lot of the probability mass is concentrated in a smaller region compared to the prior. And we'll also see that the corresponding the predictions are also much closer to what was observed in the data. So I've zoomed into the posterior here, and we can see more clearly that the predictions that we are now making are matching much more closely to the data. Of course, there is also some scatter around it because the model is inherently not a perfect representation of the structural system from which we generated the data. In addition to that, there is also measurement noise. So all of this makes it really hard to estimate parameter values. But Bayesian inference allows us to consider uncertainty in the estimated parameter values, which are represented here by the posterior probability distribution of first of all of the parameters here, and then the corresponding predictions of the time period. So let me see if quoFEM has completed. So since we only requested 2 samples, it's not able to do a good job in finding samples from the posterior. So that's why you would see that there isn't any standard deviation yet. But this shows that we were able to use quoFEM with the Matlab model and are able to use are able to do UQ with that. Now the same model can also be used for doing forward propagation also. So I'll set the same. I want to now draw samples from this probability distribution. And I'll set this problem and I'll set it running while it is running. So once we get these samples from the posterior, what can we then do with it? So we can, after we have calibrated the parameter values of this model, let's say we have data before and after the occurrence of an event. Now we want to update the parameters after an event has occurred. So the data after of measurements after the event were used to now update the values of K1, K2, K3 that I just described using the procedure previously. Now, given the sample values of the story stiffnesses, we might be interested in then computing the distribution of some EDPs, such as the peak floor accelerations or the peak interstory drifts, when this is subjected to some sort of a ground excitation, earthquake excitation. So in this case, I'm subjecting the same model to the Rinaldi acceleration history. And I'm interested in estimating the peak floor acceleration and the PIDs of each story. And I use quoFEM again to do that. And to do this, I can draw samples. I can use the same samples of K1, K2, K3 that I obtained previously from Bayesian calibration. I can pass that in to quoFEM and evaluate these EDPs by doing a forward propagation. So the point of this figure here is just, so there are 8 EDPs. So we can see that the distribution of the EDPs are quite different from the prior to the posterior. So this has implications for all further downstream analysis, such as estimating damage and loss after the occurrence of an event. So this is one application of what you can do after Bayesian calibration. So that brings us to the end of our time. So I just want to quickly recap that over the last 2 days, we have went over quoFEM. We have seen how different FEM engines are coupled with UQ algorithms and optimization algorithms within quoFEM. So quoFEM that's why it's a powerful tool which will let you add a layer of UQ or optimization onto an existing model that you're already using in your research. So let me just finally check if, yeah, so I also now just did a forward propagation. And we can see that K1, K2 was sampled approximately uniformly, and the corresponding time periods are also shown here. So you can obtain histograms within quoFEM. So you can do some preliminary analysis, and you can also get summaries of statistics of the inputs and the outputs. So that would bring me to the end of my presentation. So thank you all for being here today. If you have any questions for us, I'll be glad to take.
Matt, before you stop, do we have a minute for me to come back with ETABS? I managed to restart it just to show people that we are not cheating and it actually runs. I think that could be interesting. So let me quickly share screen. This is going to be just a minute. And maybe we can even transition into the Q&A while this is running. So you see quoFEM here, forward propagation, the model analysis that I've shown. This is exactly the same thing that I've shown before. Nothing changed in quoFEM. We don't have any results here. And ETABS restarted. We have the frame here. And when I click run, you should see in ETABS, that this is running, I'm not touching it, and this is running the analysis remotely through quoFEM. You will see as it transitions into a modal analysis, you see the mode, and it extracts the result. This is it. So this was one analysis, and then it runs it, loads it again, changes the stiffnesses of the braces, runs the modal analysis again. So this is what's happening automatically through that script. That's all I wanted to show. And I can keep this running, and I think with that we can conclude. Thank you.
Well, we are past our hour, so why don't we conclude today's tool training on the quoFEM application. Adam and Aakash, thank you for the presentations and the insight and the examples. It's really helpful. And if you missed day one, there is a video posted on our webpage for the quoFEM tool that covers the material that Sangri presented in a different video. So thank you for joining. Thank you for the attendees for being here. And Adam and Aakash, thank you very much.